This is the second section of chapter 1, and this section is about residuals. Now you may remember from the previous section that we defined a residual as this distance here, the difference between the regression line and the actual data points. The green things here. Now some of these residuals are going to be positive because they are above the residual line, and some of these residuals here will be negative. Now what we can do is we can plot these residuals on something called a residual plot, and we use the Greek letter epsilon here to represent each of our residuals. So I'll just put here epsilon, and that's what we use for our residual. And what I've done is I've plotted here on this bottom diagram the residuals based on this regression line and these data points here. And you can see that we have positive at the top, negative on the bottom, and I suppose we can put some values along this scale here. So -1, -2. Now what we're expecting is these data points, if they can be modeled by a regression line, these data points should be randomly above and below the line. They shouldn't be like all above or all below or form some sort of pattern. They should be randomly above and below. So that means that on this residual point, these crosses should be randomly above and below the x-axis here. Okay, so I'll just put that here. Now that should suggest actually that if these points on this residual plot are not random and they tend to follow a pattern, then it sort of implies that our data points do not follow the regression line. Now we can see how good a fit, what we call a goodness of fit, our data is to the regression line by calculating what we call the residual sum of squares. And that's a bit of a mouthful, so it's shortened to RSS. Now to calculate RSS, the residual sum of squares, we do SYY, which is the first time we've used this, minus SXY all squared over SXX. Now this is in the formula book on page 24. In this section, we're only interested in this part of the formula, which is written in the formula book. But in the formula book, it also goes on to tell us that this is also equal to SYY times by 1 minus R squared. Now R we would have come across before, and R is the PMCC, the product moment correlation coefficient, which you would have come across in the stats and mechanics year 2 book. So there's a link between this RSS and the PMCC, and it's this part here. Now a couple of things about the RSS. Firstly, a smaller value means a better fit. And if we want to compare two data sets using the RSS, then the data sets must be in the same units. So if we've got two data sets using the same units and we calculate the RSS for both, we could then decide which one of those two data sets is a better fit by looking for the smaller RSS value. Smaller means better fit. So I'm guessing then if we have some sort of critical value, we could then use the RSS to do a hypothesis test about the goodness of fit of a data set with a residual line. Example 5. The table shows a relationship between the temperature T and the sales of ice cream S on 5 days in June. Here they are. So I can write down straight away that N equals 5. The equation for the regression line of S on T is given by this here. S equals negative 17.154 plus 1.9693T. And in part A, we want to calculate the residuals for the given regression line and hence find the value of P. Right, so we're going to need some sort of table to be able to work out what the residuals are. So we'll I have a first column which will be T, so we'll put down the temperatures here, 15, 16, 18, 19, 21. Second column, we'll put down our observed values of S, so that's going to be the 12.0, 15.0, 17.5, P, which we're going to work out, and then 24.0. So that's our value of S. The next column is going to be working out the value of S from the regression line here. So I'm going to put down here S values from regression line. So we're going to use our calculator to work out what those are. And then in the last column, I'm actually going to work out what my residuals are, epsilon, and that's going to go in that column. So first thing I'm going to do is to work out what are all of the S values from my regression line. Okay, so these are the values of S from the regression line, and all I did to work out those was to substitute each value of T into the regression line here and work out S. So for this value of 12.3855, just replace T with 15. When I replace T with 16, I get 14.3548, and so on. Now, next thing I'm going to do is to work out what the residuals are. Now, some of these are going to be positive, some are going to be negative. So the first thing I'm going to do is to go down the column and work out which residuals are positive and which one are negative. And I can work that out by looking at each data point, the S value, and comparing it with what I get from the regression line. If this value here is bigger than this value, it means it's above the regression line, because these are the points actually on the line. And if this value is smaller, it means that it's below the regression line. So I'm just going to go down and put the signs in first. So if I look at the first one here, 12 is smaller than 12.3, so that means it's going to be below the regression line. So I'm going to have a negative residual. Second one, 15.0, that's above the regression line, so that's going to be a positive. This one here, 17.5, is lower than this, so it's going to be below the regression line, so it's negative. This one I don't know about yet, so I'll leave that blank. But I can work out this one, 24.0, is smaller than this value, so that means it's below the regression line, so that's a negative residual. So all I'm going to do now is to work out the difference between each of these pairs of values, and that will give me the residuals. Now for some of them I don't need a calculator. So top one, I know it's negative, and the difference between the two numbers is 0.3855. I'll need a calculator for that one, which I'll do in a moment. And I think the bottom one here I can do without a calculator. That's going to be 0.2013. So I'm just going to grab a calculator and work out these other two values here. So I've just put those in. Now, if you're not happy with putting the signs in first, actually, if you just do the second column minus the third column, that will give you what the residual is, and that will always give you the correct sign. So if we call this square, that column, and this column triangle, then we can get this by just doing that column, the squared column, minus the triangle column. So this column minus that column will always give you the correct sign. And actually the advantage of doing that is I can now fill in this residual, because it would be this value minus this, so I can write it down as P minus 20.2627. Now, I'm not sure if I mentioned it before, but I did on a previous video. The sum of the residuals equals 0. So the sum of epsilon equals 0. I've got two epsilons there. That should be the sum of. So we know that the sum of these equals 0. Then we can use that to work out the value of P. So we'll just write that down. That negative 0.3855 plus 0.6452 minus 0.7934 plus P minus 20.2627 minus 0.2013 equals 0. We just need to solve that equation to find P. Okay, so if we simplify that, we'll end up with negative 20.2627 20.9977 plus P equals 0. So that will give us P equal to 20.9977. Is the exact value. I suppose we could give it to 3 significant figures and say that P equals 21.0. That's 3 significant figures. So now we can work out the residual for 19. So basically we're working out what the residual is for this value now that we've got the value of P, and that's going to be our value of P, which is, we'll use the exact value, 20.9977 minus the value of S we got from the regression line, which was 20.2627, and we get a residual value of 0.735. So let's just highlight our value for P here. That's the exact value. There's the 3 significant figures, and this is what we get for the residual for 19. So we can finish off part B by considering the residuals, comment on whether a regression model is suitable for these data. So is there a pattern to whether they're positive or negative residuals? Are they randomly distributed? Well, let's just highlight them. So the positive ones we'll highlight in red. So that's not positive, but this one's positive here. And we worked out the residual for 19, that was positive. And then these two were negative. So we've got like negative, positive, negative, positive. They seem to be randomly distributed around the regression line. So I would say, yes, it is a suitable model. It's difficult to tell because we've only got a few data points. A regression model is suitable since the data points seem to be randomly distributed about a regression line, because we've just got this pattern of well, no pattern, but just positive and negatives. So I've just summarized what we said down here. Example 6. The table shows the time taken, T minutes, to produce Y litres of paint in a factory. So there you go here. The regression line of Y and T is given as this equation here. So let's just highlight that. One of the Y values was incorrectly recorded. Calculate the residuals and write down the outlier. So what we're looking for is going to be a Y value that has a large residual. So we'll do a table to work that out. Okay, so here's our table. What we're going to do now is to substitute these values of T into this equation here and work out what the values are from this regression line. So these are the exact values that we got from our calculator here. Now we're going to work out the residuals epsilon by just doing this value minus this value, and that will give us the correct sign as well. Okay, so here's our residuals calculated here. I just corrected this value. I think I put 26 before. It should be 25.86048. And we want to write down the outlier. So look at the residuals. Now this one is way bigger than the others. So I would suggest that the outlier is this value here. Now, since we were working out the residual basically from the Y value, it's the Y residual, so the residual in this direction that we've worked out, then the outlier would be the Y value, because that's the residual, so not the T value, but the Y value here. This T value could be correct actually, but this Y value here could be incorrect, the outlier. So part B, comment on the validity of ignoring this outlier in your analysis. Now, we could give a couple of answers for this. We might argue that we should include this data value here, since there are only 5 pairs of data values, and by removing one, we're literally removing 20% of the data we've got. Or we could argue that it should be removed since its residual stands out from the others, it doesn't fit the pattern of the other residuals. Part C says, ignoring the outlier, produce a new model. Now we're not going to work out the regression line from scratch. What we're going to do is we're going to scrub this value here that we said we're going to ignore, and then put the rest into our calculator. So if you've forgotten how to do that, on your calculator go to Menu, 6, then press 2, then we're going to enter our data, then press the Option button, OPTN, under Shift, then 4, and then it will give you the values of A and B, and they're quite long here, so I'm probably going to give my answers to 4 decimal places, something like that. Let's see what we've got. So we'll have Y equals, now the value of A I've got is 10.66905, so let's call it 1 there, plus B, and my B is 4.357, let's say it's got 26, so let's call it 3x. So I'll just put that A and B are to 4 decimal places, and I just need to remember that it shouldn't be X here at the end, it should be T, because T is on the top row. So let's just highlight that before we move on to part D. And part D says, use the new model to estimate the amount of paint that is produced in 4.8 minutes. So this is pretty straightforward. This is just substituting the time of 4.8 into this equation here. So it's going to be Y equals 10.6691 plus 4.3573 times by 4.8. Let's see what we get for a value of Y. And that gives us 31.58414 litres. So we give that to 3 significant figures. So we'll do that as 31.6 litres. And we'll just highlight that there. Example 7. The data shows the sales in hundreds Y of slush at a riverside cafe and a number of hours of sunshine X on 5 random days during August. So N is 5 here. Now we've been given some sums here, and what we need to do in part A is to calculate the residual sum of squares for this data. So remember, RSS, the residual sum of squares, is equal to SYY minus SXY all squared over SXX. Now remember, this is in the formula book, and in the formula book as well is how you work out these summary statistics as well. So I'll write out the full formula. So SYY is going to be the sum of Y squared minus the sum of Y all squared over N. So that's our SYY. And then we need to subtract, and it's going to be quite big here, the sum of XY minus the sum of X times the sum of Y over N. And all of that is going to get squared, divided by the sum of X squared minus the sum of X all squared over N. Now these values I believe are all given here, so we can just substitute them in. So the sum of Y squared is 371.75, and then we're going to minus the sum of Y, which is 42.9. That's going to be squared over N, which is 5. So that's our SYY. Might be a bit of a struggle to fit in the rest. We see how we go. The sum of XY, which is 467.45, minus the sum of X times the sum of Y, I think we are going to run out of space. So I'll tell you what, let's do that down here. So this carries on like this. So yeah, where were we? Sum of xy 467.45 minus the sum of x 53.7 times 42.9 over 5, and then that is all going to get squared, and we divide that by the sum of x squared, which is 589.09, minus the sum of x 53.7 squared over 5. So we can just type the whole lot in on my calculator and see what that gives us. Okay, what I actually decided to do was to split the calculation up because it was too much to type in. So this is SYY, this is SXY, then we square it, and this is SXX. So calculating that would be easier. So 0.0294305 and so on. So I'll probably want to give that to 3 significant figures. So let's call that 0.0294 for our value of our SS. Okay, part B. The RSS for 5 random days in December is 0.562. So this is December, this is August. State with a reason which month is more likely to have a linear fit between the number of hours of sunshine and the sales of slush. Well, a smaller RSS means that our data is closer to the residual line, and this is a larger value. So remember we said smaller is better. So I'll just put down here that since 0.0294 is less than 0.0562, August is more likely to have a linear fit between the number of hours of sunshine and the sales of slush. So you should now be able to do exercise 1C on pages 14 to 15 of the textbook.